Sectional President, and thank you, Chair, for nice introduction. I will be talking about the nanostructured materials for modern charge storage and conversion applications. The different type of energy systems available today, they are electric field based, electrochemical, energy harvesters and mechanical, and among them I will be focusing on electrochemical one. The electrochemical capacitors, because of their small size and extraordinary performance, they are known as supercapacitors also. So this is electrochemical capacitor. What is a supercapacitor? Maybe a new term for some of the delegates sitting here. You can say it is a device between conventional capacitors and batteries in design as well as in performance. Why we need supercapacitors when we are having so advanced batteries? Because for short charge discharge time, when weight is the critical factor, specific power is more important than specific energy. So the applications which need high thrust, high power, they need short discharge time, and for that this type of devices are very useful. For example, in aerospace launch applications and missile applications. If we compare the different type of devices which are available in terms of a Ragon plot, then we plot here specific energy versus specific power. You can see the fuel cells are the best options when we use in application which is having high specific energy, which require high specific energy. But for application which need high specific power, then capacitors are the best one. But you can see the supercapacitors occupy major chunk of this Ragon plot. So anybody who is working in this area has a ambition or goal to increase specific energy and specific power in a single device, and that is the main motto of working on this type of energy storage system. When we compare them to batteries, the power density is low, energy density is high in case of battery, but supercapacitors they have high power density, moderately high energy, lifetime maximum 3 to 4 years, but they can perform very long time. The temperature dependence in cold climatic conditions, it is hard to start a diesel driven vehicle and it takes the life of the battery, but they are independent of the temperature. So specific energy and specific energy is the main focus we have to increase, and we have to design materials, new materials which can have this type of attribute. Means they can be charged and discharged fast, outstanding cycle life, high power, low energy density is the drawback, and cost. For any device to make to be that commercially compatible in comparison to the existing storage devices, we have to reduce the cost of the device. So we have to reach highest energy and power density to increase the cycle life, to get smallest component volume and weight wise, and to reduce the electronic series resistance, and of course the cost I have already discussed. The different type of materials which are being used in supercapacitors, they are the carbon materials, activated carbon, graphite, carbon fibers, and CNT graphenes are the latest additions. Pseudo-capacitors, they use metal oxides and conducting polymers, and hybrid capacitors, they use combination of these all materials, and I will be discussing the examples using different type of combinations and hybrid capacitors. When we talk of activated carbons, then there are so many advantages: cost, chemical stability, electronic conductivity is very good. Activated carbons, fiber, they are better as compared to activated carbons because of their lower electronic series resistance, but the disadvantage is narrow pores and low electron conductivity and low energy density. So we have the restriction of using limited number of electrolytes when we are using activated carbons. So we have to design we have to focus different other type of materials. The conducting polymers are one of them, and they came into limelight in the year 2000 when these three gentlemen were awarded Nobel Prize for discovering conductivity in a plastic material, and the metal oxide. Ruthenium oxide is the best one reported till date in terms of capacitance, but the cost is very high and we aim to reduce the cost. So, the three materials which are being used are carbon, metal oxide and conducting polymers. The conducting polymers is the latest addition. Why conducting polymers? Because polyaniline and polypyrrole, these are the two most worked upon conducting polymers. Reason, the switching time between two cycles, two redox cycles, the switching time is 100 millisecond, repeatability million times before any degradation, and change in the impedance by a factor of 3 in case of polyaniline and 10 in case of a polypyrrole. So, these are the best parameters for energy storage devices which are available in case of conducting polymer. So, we can have the combination of these a new way to increase the specific energy carbon materials, and for long pulse applications we need either metal oxide or conducting polymer, so that we can have surface nature of polymers and electronic conductivity or electric conductivity of the original carbon intact in a single material. So, synergy type of application we are focusing. Three examples I will be talking about. One in which metal oxide and this conducting polymer and carbon substrate, all these combined together. This is the carbon substrate. Upon that we polymerize polyaniline. We have to define the parameters or control the parameters. So, we want to control the polymerization to oligomeric state, only to oligomeric state, and upon that the nickel cobaltate is deposited. So, this is a 3-in-1 type of system. The different conditions have been applied and the optimized conditions are before you. We have tested this different samples. In that, aniline and carbon nanotube component is constant, only this component is varied. The reason for that variation is we want to have highest aspect ratio and particular morphology, so that can be obtained using different concentrations of this nickel cobaltate in this case. I have to skip these results, XRD and EDX studies here. This will give the idea. If we focus here, the third one, this is having a different morphology as compared to the other one. For example, the sharp tips and needles are observed with the formation of flower-like microspheres. So, using this concentration, we can obtain this type of morphology which is very much desired. The reason was I already explained aspect ratio, which facilitates the charge transport and ion diffusion in a better manner. HR10 pictures with this proves the crystalline character of the structure, because carbon nanotubes are having crystalline nature, and we want at nanoscale when the material comes in the either it is metal oxide or conducting polymer, it will have crystalline nature. So, more synergy we can achieve in the among the three components. Electrochemical studies, cyclic voltammetry. You see here, in this material we are having highest specific capacitance from cyclic voltammetric studies as well as from charge discharge studies. So, this particular type of morphology is helping the diffusion of electrolyte ions up to the among the three components in the electronic material which we have designed. When we test it for cycle life, because to have the higher cycle life is the main aim for making the material into a device. So, we retain after 500 cycles 83% of a specific capacitance in the third composite material, and the electronic series resistance from this plot is also a minimum in this case, the third composite material. Conclusion, to skip that. The second example I will be focusing on doping of the metal on metal oxide using conducting polymer and carbon nanofiber here. Instead of carbon nanotube, we have tried nanofibers, and we have made binary and ternary composite materials in that. Simple laboratory facilities available in the chemistry laboratory. We have controlled the different parameters, and we have obtained binary metal oxide and ternary composites. You see here. Here we have taken the carbon nanofiber as substrate. Upon that, before making the metal oxide hydrothermally in the form of a layer, upon that we have acetated the carbon nanofiber. The purpose was to have functional groups at the ends and the other deformities, so that we can have better binding by introducing these groups, hydroxyl and carboxylic groups. We can have better binding of the metal oxide with the carbon substrate, and on that binary composite we have deposited this conducting polymer. So this is the ternary composite, and as expected, it had best results among the three. These are the spectra, and you see this is the final morphology, in which we are having the three components: metal oxide, carbon nanofiber and the conducting polymer. The results, again the focus was to have minimum concentration and to get the crystalline structure. Cyclic voltammetric studies prove that the ternary composite gave best performance in terms of specific capacitance, farads per gram. So this is quite high as compared to the binary one. In terms of charge discharge, again the best results are obtained in case of the ternary composite. Also, about 85% of the retention in capacitance was there, 87% after 500 cycles. I have to wind up. Okay. This is third example. We have taken vapor grown nanofiber here. In earlier two cases, we have tried with acidic electrolyte. Here we have taken aqueous potassium hydroxide as electrolyte. Here we have taken the changed the substrate as well as the current collector. In earlier cases, I explained the current collector was graphite electrode, and here the nickel form we have taken as current collector, and intentionally the electrolyte is potassium hydroxide. I will skip the results, and I will focus on certain points here. The aim is to have thinnest layer of the conducting polymer on the vapor grown nanofiber, and by reducing the concentration of the monomer in the initial polymerization solution, we are able to achieve less than 10 nanometer thin layer of the conducting polymer on the vapor grown carbon nanofiber surface. Here you can see the thinnest layer, which was less than 10 nanometer. It is having the best reversible voltammogram in terms of oxidation redox cycles, and you see it is showing the maximum retention even at high scan rate. For this type of conducting polymer composite, we can use for high power applications also. Okay. Normally, the reported literature shows that after 13,000 cycle number, the capacitance goes down, and we expected that it should be like that, but even after 25,000 cycles, it was increased capacitance. Why we observed, or why we believed that? Because the conducting polymer undergoes degradation after continuous recycling. The results are clear by the SEM images. You see here it is, the surface is quite smooth here. Further magnification will prove that the conducting polymer layer is now peeled off. You can see the backbone chain is now broken. Then why we are getting increased capacitance? The reason is when the conducting polymer layer develops cracks, now the electrolyte potassium hydroxide can percolate deep up to the current collector nickel form, and nickel hydroxide couple comes into picture. So 3-in-1 system again is demonstrated by using this carbon nanofiber, which is vapor grown, and we are having the best results when the layer is thinnest. The reason can be the penetration depth can be developed by the ions in polypyrrole layer here below 10 nanometer, and to obtain fully reversible fast redox behavior. So, most mass of the conducting polymer can contribute to pseudo capacitive charge storage. So, I skip these, and the financial assistance from these agencies I acknowledge my collaborators, and most important, thank you all.